So the zero question is what is PHIP-SAH? So let's quickly go through the different passages of this hyperpolarization method that allow to polarize molecules that contain a carboxylate group, although yesterday we saw that also nitrate group can be polarized. So if we have molecules that contain a group that can be functionalized with unsaturated alcohol, we can obtain this kind of substrate that can be hydrogenated using parahydrogen. I use parahydrogenated just for shortness, but hydrogenated using parahydrogen is more correct. Then we can transfer spin order from parahydrogen protons to a target heteroatom, usually carbon-13, on the target substrate. And in the end, by means of a hydrolysis step, we can obtain the target hyperpolarized molecule in the best situation in aqueous solution, while the other passages can be carried out in an organic solvent that is much more good for hydrogenation catalysis. So the first true question is, what can we polarize? So it seems a trivial question, since we told that we can polarize molecules that contain a carboxylate group. So we can polarize a molecule like pyruvate, acetate, but also lactate, maybe amino acids or other. So molecules that cannot be produced from direct hydrogenation, so by means of hydrogenative PHIP. But the main issue is how much polarization can we obtain on these molecules, and can we go through all the steps of the PHIP-SAH method and obtain those molecules in an aqueous solution that can be used for in vivo applications? Well, for pyruvate, it is true, so we can go through all those steps. For other substrates, it depends. The final solution can or cannot be used for in vivo applications, since maybe the concentration of organic solvents is too high. For other molecules, for example, amino acids derivatives, the functionalization of the substrate that is needed to obtain a molecule that can be hydrogenated cannot be completely removed to obtain the target product. For other substrates, we have to consider all the single steps of the PHIP-SAH method to decide if we can or cannot use these molecules for our purposes. One of the most issues of the most important questions at this point is how much polarization can be obtained. And I'd like to add how much molar polarization, so how much the molar polarization is the product of the molar concentration and polarization of a molecule, and is most important if you want to use these substrates for in vivo applications. And I will shrink all the field to our favorite substrate, that is pyruvate, because we will see, and we have seen that hyperpolarization of pyruvate strongly depends on the conditions and on the precursors that are used to obtain it. And looking at all those components allow to find out which can be the issues in hyperpolarizing molecules using PHIP-SAH, and so can also allow to increase the application of this method. So how much molar polarization can we obtain on pyruvate? Molar polarization depends on the fact that we are able to obtain a complete hydrogenation of a concentrated batch of substrate in a few seconds. Depends on the fact that we transfer completely the para-hydrogen spin order to the product. Depends on the method that is used for spin order transfer from para-hydrogen protons to carbon-13 or to the heteroatom once that the substrate has been hydrogenated. And depends also on how much hyperpolarization survives to the final step, that is hydrolysis and workup of the product. So let's consider which are the different conditions in which pyruvate and in particular propargyl pyruvate can be hydrogenated at a high concentration. Of course, we need to use high pressure of hydrogen and high temperature, even if not so high. Actually, 7, 8 bar are more than enough, and temperature around 70, 80 Celsius in our cases. If we use a rhodium catalyst, that is a cationic rhodium catalyst that is usually applied for this kind of application, we can obtain complete hydrogenation of 0.5 molar solution of propargyl pyruvate using about 2% of rhodium, and 4% of catalyst must be used if we want to obtain a complete hydrogenation of vinyl pyruvate in a few seconds. What is important to consider is also the solvent in which the reaction is carried out. In this case, we can use those concentration if we use acetone as a hydrogenation solvent. If we change solvent, if we use chloroform, for example, concentration of catalyst must be higher for both propargyl pyruvate and vinyl pyruvate. Why? Because acetone is a coordinating solvent that enter into the reaction, while chloroform does not enter into the catalytic reaction. As we can see from this scheme. So this is the catalyst that contains here two ligands, the activated catalyst that can be solvent or another ligand, for example, phosphine. Then the reaction proceeds through replacement of the solvent with the substrate, and in the end the solvent enters again into the reaction pathway. So the solvent is quite important for the hydrogenation efficiency, and this is why in acetone the catalyst efficiency is much higher. We have recently published a work in which we showed how we can significantly decrease the concentration of catalyst in chloroform for hydrogenation using an adjuvant that is simply a triphenylphosphine. So how much molar polarization we can obtain depends on the solvent that is used, the amount of catalyst that is used for hydrogenation. Of course, the higher the catalyst hydrogenation, the higher the residues of rhodium in the final aqueous solution can be. Then the molar polarization that we can obtain depends on the singlet order that is transferred from para-hydrogen to the product. we can obtain information about how much singlet order is transferred to the product directly from proton NMR spectra that are obtained in the so-called Altadena experiments. Here are reported two Altadena experiments carried out on ethyl pyruvate and allyl pyruvate. And from these proton spectra, we can state that the polarization level is significantly stronger on allyl pyruvate rather than ethyl pyruvate, and therefore also carbon-13 polarization that will be transferred from perhydrogen protons will be for sure lower for ethyl pyruvate rather than on allyl pyruvate, simply because the amount of singlet order that is transferred to the allyl pyruvate is higher than that on ethyl pyruvate. And this is again due to the hydrogenation reaction. So during the hydrogenation, an intermediate is formed during which the singlet order of perhydrogen can be partly mixed with the triplet state. And so the singlet state that is transferred to the product is not 100%, so it's not the same level as it was at the beginning in the para-enriched hydrogen. Then let's proceed. How much polarization we can obtain on pyruvate depends, of course, on the spin order transfer step. We now want to consider spin order transfer from perhydrogen protons to carbon-13. It must be mentioned that there is some spontaneous spin order transfer from perhydrogen protons to heteronuclei. And in fact, we can also observe antiphase signals, so spin order on heteroatoms, without doing anything after pyrohydrogenation at low magnetic field. But if we want to obtain net magnetization, so if we want to obtain a signal that can be used for MRI purposes, for example, we must obtain net magnetization instead of spin order. There are different methods that allow to obtain that and also to increase the amount of hyperpolarization on the heteronucleus. Our favorite one is magnetic field cycle. So let's see how it works. We can make the perhydrogenation reaction at the geomagnetic field, so out of the NMR spectrometer. And then we need a setup that is made of a mu metal shield and a generator of pulses that allow to control the magnetic field intensity inside the mu metal, so that when we carry out the hydrogenation at geomagnetic field, the weak coupling condition between proton and carbon-13 is obtained. When we transfer our sample within the mu metal, isotropic mixing between proton and carbon can be obtained, and then we transfer the sample within the magnet and we obtain net magnetization on the heteroatom. What about hyperpolarization of pyruvate? Here we consider allyl pyruvate because, as we told before, this is it has a higher spin order, so higher proton polarization than vinyl pyruvate. What is important is the magnetic field cycling step, and in particular the remagnetization step. So what happens when we place our sample within mu metal and apply what is called magnetic field cycle. So the magnetic field is dropped quickly, so non-adiabatically, to almost zero, then is slowly brought back to higher magnetic field. What can we do is to manipulate the remagnetization profile so that if we use a tailored remagnetization, the magnetization, the net magnetization of carbon-13 is increased significantly. What is also quite important is to control the strength of the nearly zero magnetic field that has to be lower than a few tenths of nanotesla, so about 30-20 nanotesla. And this is not always not easy, but even possible with our setup. Okay, so magnetic field cycling is another factor that determines how much molar polarization we can have, pyruvate. How much hyperpolarization can survive to the hydrolysis step and work up. So let's see what we have to do. We have to quickly add the base solution to the organic solution. An emulsion is formed and it quickly separates, and we obtain hyperpolarized pyruvate in the aqueous phase. What is the polarization drop during this hydrolysis step? If hydrolysis is carried out with a protonated base, so with sodium hydroxide, the polarization loss is rather significant. We have almost half of polarization after hydrolysis, while the losses are less big if deuterated base is used. So in the end, how much molar polarization we can obtain on pyruvate, considering that the concentration that has been obtained is in the order of 50-60 millimolar. 2-3 millimolar hyperpolarized pyruvate has been obtained. And the big question now is that enough for doing imaging in vivo? Let's see.
In the interest of time, could you just take just a few more minutes to finish?
Yes, sorry, I was a bit out of time. Yes, a couple of minutes. So how much molar polarization we need for carbon-13 MRI? Here we made a phantom with urea and observed that 0.05 millimolar is enough to obtain these images with this spatial resolution, so 1 millimeter pixel having a slice thickness of 5 millimeter, while if we want to make chemical shift imaging, the spatial resolution is worse. Of course, this is quite less than what we have with hyperpolarized stuff. And in fact, we had been able to acquire a single shot carbon-13 flash images using the pyruvate solution injected in water. And also to say that spatial resolution can be rather good, we also injected the hyperpolarized pyruvate solution through a capillary tube and obtained this image, carbon-13 image, using hyperpolarized pyruvate diluted in an aqueous solution. Concerning in vivo imaging, well, is a matter more of biocompatibility at this point, actually, but that these images, anatomical images, have been obtained. So, in summary, what are the answers of all of these three questions? Not all so easy. So what can we polarize? Many molecules, but it depends on what we want to do with these molecules, if just polarizing or using them for some biological application. How much molar polarization can we obtain on pyruvate? Also here, it depends on many factors, on hydrogenation solvent, hydrogenation condition, on the substrate, the kind of derivative that we use, on the spin order transfer technique, and so on. Is that polarization enough for imaging and also in vivo? Now the answer is yes, but there is much space for improving, of course. There is always space for doing better. So in the end, thank you for listening, and also to all the people who worked on those topics during the years.
All right, thank you very much.